In April 1944, at a single factory in southern Michigan, the Ford Motor Company built 453 four-engine heavy bombers in 30 days. 2 9-hour shifts, 6 days a week, 468 working hours total. One finished B-24 Liberator rolled off the line every 63 minutes. At its absolute peak, Willow Run was producing one bomber every 55 minutes, 26 aircraft per day, 650 per month, for a war that was being fought on the other side of 2 oceans. Stop and consider what that number means. A B-24 Liberator was 67 feet long, weighed 18 tons, and consisted of more than 450,000 individual parts. It had 4 engines, 10 machine guns, 3,000 pieces of cut wire totaling 5 miles in length, and 360,000 rivets in 550 different sizes. Every one of those rivets had to be installed correctly, in the correct position, by hand, by a human being, in a precise pattern that determined whether the airframe would hold together at 20,000 feet under enemy fire. By the math of the previous decade, this should have been impossible. The traditional way of installing aircraft rivets, buck riveting, required 2 skilled workers per rivet, one on each side of the metal. The man drafting plans in 1939 to mass-produce a B-24 in this way could write down the labor requirement and watch the number defy reality. By 1942, every able-bodied skilled worker in the United States was being drafted into the military or pulled into shipyards. The pool of trained metal workers required to assemble bombers at industrial speed simply did not exist. Germany, working on the same problem with the same technology, never solved it. In July 1944, the captain of the world's first jet bomber unit complained that the aircraft his squadron received from the factory arrived covered in defects. Defects, he said, were caused by hasty assembly and a shortage of skilled labor in the plants. He was describing the exact problem that Ford had solved 3,000 miles away. The solution had been built in a small brick building on White Street, on the bank of the Detroit River, by a man named Louis Huck, and it had nothing to do with assembly lines or labor pools or industrial genius. It was a single, unglamorous fastener, a piece of metal smaller than a fingernail, that changed who was allowed to build airplanes. This is the story of that fastener.
To understand why the Huck Rivet mattered, you first have to understand what a B-24 Liberator actually was as an industrial object. The Liberator was the most produced multi-engine aircraft in the history of the United States. Across all factories, Consolidated in San Diego and Fort Worth, Douglas in Tulsa, North American in Dallas, and Ford at Willow Run, 18,482 were built between 1940 and September 1945. Ford alone built somewhere between 8,645 and 8,685 of them, depending on which official Ford or Henry Ford Museum source you consult. That is roughly half of the total wartime production of the type, manufactured in a single building. The aircraft itself was an industrial nightmare disguised as a weapon. 67 feet long, with a wingspan of 110 feet, 18 tons empty weight, 8,000 pounds of bomb capacity in 2 large bays, 4 Pratt & Whitney radial engines each producing 1,200 horsepower, 10 .50 caliber machine guns, a crew of up to 10 men, and a maximum range of around 3,000 miles. By comparison, an automobile of the same era had roughly 15,000 parts and weighed 1,500 kilograms. A Liberator had 450,000 parts and weighed 12 times as much. 360,000 of those parts were rivets. Different sources give slightly different numbers. The Ford documentary on Willow Run cited about 400,000. The Consolidated specification document cited 313,237, and one historian who restored a flying B-24J in 1989 had to replace more than 420,000 rivets just to bring the airframe back to flying condition. The exact count varied depending on the variant and the production run, but the order of magnitude is consistent. A liberator was held together by something on the order of 350,000 to 400,000 small metal fasteners distributed in 550 different sizes, every one of which had to be installed correctly. A special forging department at Willow Run produced 7 million rivets per day to keep up with the assembly line. That number, 7 million per day, describes the scale of the problem and the scale of the solution simultaneously. A bomber had 400,000 rivets. Willow Run was producing roughly 1 bomber per hour at peak. That requires approximately 400,000 rivet installations per hour, every hour, around the clock, 7 days a week. 8 people working a single rivet, even 1 rivet per minute, would take a calendar year to finish a single airplane. Something about the way the rivets went in had to change.
In the early 1930s, a young American engineer named Louis C. Huck was working for General Motors. Part of his work brought him to Germany, where he spent time at the Dornier Aircraft Works, one of the most respected aviation companies in Europe at the time, builders of the famous flying boats that linked the continents in the golden age of long-distance air travel. What Huck saw at Dornier was a bottleneck. The bottleneck was riveting. The standard method of installing a rivet in an aluminum aircraft skin had not changed in any fundamental way since the technique had first been adapted from shipbuilding in the early 1920s. The rivet was placed through aligned holes in 2 pieces of metal. One worker on one side of the joint applied a pneumatic hammer to the rivet head. A second worker on the other side of the joint held a heavy steel block called a bucking bar against the protruding end. The hammer drove the rivet. The bucking bar deformed the back end into a mushroom that locked the joint, and a strong, vibration-resistant connection was made. This method worked. It produced extremely high-quality joints. It had 3 problems that made it ill-suited to mass production. First, it required 2 workers per rivet. 2 skilled workers, in fact, who had to coordinate their actions through millimeters of metal that neither could see through. The bucking bar held against the back side of an aircraft skin had to be precisely aligned with the right amount of pressure in the right plane. Too soft and the rivet would not set, too hard and the metal would deform. The sound of the hammer would tell an experienced operator whether the connection was good. An inexperienced one would produce defective rivets all day without realizing it. Second, it required access to both sides of the joint. For a flat panel of aircraft skin, this was tedious but possible. For an aircraft wing, where the inside of the structure was a labyrinth of spars and ribs, often the only way for a bucker to reach a rivet's blind side was to crawl into the wing through an inspection hatch and work in a confined space, sometimes upside down, in temperatures that varied by season and could exceed 40 degrees Celsius in a closed metal cavity. Third, it required skilled workers. Bucking was a craft. It took months of training to do well and years to do quickly. In peacetime, the supply of such workers was adequate. In wartime, the supply collapsed. Huck watched the Dornier engineers struggle with this bottleneck and saw with the clarity of an outsider what the problem actually was. It was not a process problem. It was a fundamental geometry problem. As long as the rivet required access from both sides, the assembly process would always require 2 workers, both of whom needed to be skilled, and one of whom would always be working in some uncomfortable corner of the airframe. The Great Depression ended Huck's time in Germany before he could try out his proposed solution at Dornier itself. He returned to the United States, took the problem with him, and in 1936 was granted a patent on a structural blind rivet. The word blind was the entire point. The rivet was set from a single side. The other side, the blind side, required no worker, no bucking bar, and no access at all.
By 1939, Louis Huck was confident enough in his invention to start a business around it. He rented a small building on Wright Street on the bank of the Detroit River and began manufacturing his structural blind rivets. The Huck Manufacturing Company was incorporated the following year in 1940. The timing was, for purposes that nobody in 1940 could fully foresee, perfect. The mechanism of the Huck rivet was elegant. The fastener itself consisted of two pieces, a hollow body, often called the sleeve, and a pin, called the mandrel, which passed through the center of the sleeve. To install it, an operator pushed the rivet through aligned holes in the metal panels and engaged the mandrel head with a pneumatic tool, what the Huck company called a pneumadraulic installation tool. The tool clamped onto the mandrel and pulled hard. The mandrel head, drawn back through the sleeve, forced the sleeve to bulge outward on the blind side, forming a new head against the back of the joint. When the bulging was complete and the joint was locked, the mandrel snapped off at a designed weak point. The leftover stub broke away. What was left in the metal was a finished, structural-grade fastener set from one side in approximately 1 second. The implications of that 1 second were enormous, and they were not primarily about speed. They were about who could do the work. A traditional buck rivet required a skilled hammer operator and a skilled bucker. A Huck rivet required an operator who could line up the tool, squeeze the trigger, and remove the broken mandrel stub. The training time collapsed from months to a few hours. The labor pool that could install the fastener expanded from a small population of trained metalworkers to virtually anyone with hands. And the access requirement, the geometric constraint that had forced workers to crawl into hot, dark cavities of aircraft structures with bucking bars, disappeared entirely. A Huck rivet could be installed in a wing skin from the outside of the wing, with no access required to the interior at all. In 1939 Detroit, this looked like a useful incremental improvement to an industrial process. By 1942, it looked like the answer to a question that the entire American war effort was struggling to ask. When the United States entered the war in December 1941, the country had a problem that nobody had quite anticipated. The factories existed, the raw materials existed, the contracts had been signed, the aircraft designs had been finalized. What did not exist in anything like sufficient quantity was the trained workforce required to build modern aircraft at industrial scale. Skilled metalworkers, men who had spent years apprenticing in shipyards, in machine shops, in the pre-war aircraft industry, were the same population the Army was drafting. Every man pulled into uniform was a man not available to install rivets. By 1943, the demographic crisis in industrial labor was acute enough that the federal government was actively recruiting groups that the pre-war economy had largely excluded. Women were the obvious candidate. Black workers, in numbers that the segregated industries of the 1930s would never have hired, became suddenly indispensable. The cultural icon of Rosie the Riveter, the woman in a red bandana with a flexed arm above the slogan, "We can do it," emerged in this period not as a gesture of social progress, but as a recruiting tool. The factories needed women on the line because the men were not there to staff it. Henry Ford himself was famously, almost ideologically, opposed to hiring women. He held that line until the demographic mathematics defeated him. By 1944, women constituted roughly 40% of the Willow Run workforce. The plant employed approximately 42,500 people total, of whom about 12,000 were women, paid at the same rate as their male counterparts, 85 cents per hour. Some of those women filled supervisory roles. Some of them flight-tested completed bombers. The plant also employed 10 people from the entertainment industry, recruited specifically for their small stature, who could climb inside wing cavities to perform riveting work in places where average-sized adults could not fit. This was a workforce that could not have built B-24s by traditional methods. The traditional method required 2 skilled buck riveters per fastener. The supply of skilled buck riveters in 1943 America was, for practical industrial purposes, 0. Ford could not draft them, Ford could not train them in the time available, Ford could not import them. What Ford could do was install Huck rivets. The first precision-engineered Huck blind rivet was installed on a B-24 Liberator at Willow Run in the summer of 1943. By the end of that year, every Liberator coming off the Willow Run line was using them. The fastener that Lewis Huck had patented in 1936, for reasons that had nothing to do with the war that did not yet exist, was suddenly the technical solution to the most acute labor shortage in American industrial history. The change was not announced with a press release. It was integrated into the production process, recorded in engineering memos, and absorbed into the daily rhythm of an assembly line that was ramping toward bomber-an-hour output. The women on the line did not need to know that what they were holding was the product of an American engineer's observation of a German aircraft factory in the early 1930s. They needed to know how to align the tool and squeeze the trigger. The clearest illustration of what the Huck Rivet did to aircraft manufacturing comes from a comparison of two factories building the same airplane. Consolidated Aircraft in San Diego was the original manufacturer of the B-24 Liberator. They had designed the airplane. They built it the way airplanes had been built throughout the 1930s, in open hangars, often outdoors under the California sun, with hand-fitted parts, traditional buck riveting, and a workforce of skilled craftsmen. By the standards of pre-war aircraft manufacturing, Consolidated was a competent and respected operation. By the standards of 1943 industrial mathematics, it was unsustainably slow. When Charles Sorensen of Ford visited Consolidated's San Diego plant in early 1941, what he saw alarmed him. The B-24's center wing assembly, a single large structural component that joined the two outer wings to the fuselage, was being built using a method that required, by Sorensen's own account, on the order of 250 hours of skilled labor per unit. 250 hours, roughly 6 full work weeks for a single team to produce a single subassembly. Sorensen sketched out that same evening a different way of doing it. Ford's adapted process at Willow Run, eventually using Huck rivets and assembly line breakdown of the wing into smaller subassemblies built in parallel, brought the labor time on the same center wing assembly down to approximately 1 hour. 250 hours to 1. A factor of 250. The number is so striking that anyone hearing it for the first time should be skeptical, and skepticism is appropriate. The figure compares Consolidated's craftsman-built process to Ford's fully optimized assembly line process, and the Huck Rivet was one of several factors enabling the difference. But it was a meaningful factor. The blind fastener allowed subassemblies to be built in parallel by unskilled workers, then mated to other subassemblies on the line, with riveting performed at the integration step rather than as a continuous bottleneck running through every stage of construction. Consolidated, watching what Ford was doing, eventually adopted many of the same techniques. Their own production rates improved. By the end of the war, the 4 factories building B-24s, Consolidated in San Diego and Fort Worth, Douglas in Tulsa, North American in Dallas, plus Ford at Willow Run, were collectively producing the most built American military aircraft in history. But Ford alone built half of them, and Ford's rate, when it hit full stride in April 1944, was 453 airplanes in a single calendar month. 1 every 63 minutes around the clock. At absolute peak, the figure quoted in the Ford Motor Company's own documentary about the plant was 1 B-24 every 55 minutes. The fastener was not the only reason for that number. Sorensen's adaptation of automotive assembly line principles, the moving conveyor system designed by architect Albert Kahn, the breakdown of the bomber into 69 separate subassemblies, the federal investment of $47 million in the building itself, all of these contributed. But the fastener was a necessary condition. Without something that an unskilled worker could install in 1 second from one side of a panel, the Sorensen-Kahn process would have collapsed at the riveting stations into the same bottleneck that had been bleeding Consolidated's productivity in San Diego. The Hellcat fighter, built by Grumman for the U.S. Navy and a key contributor to American air superiority in the Pacific, also adopted Huck rivets in its production. Other manufacturers followed. The blind fastener became, by 1944, a standard component of American wartime aviation manufacturing, embedded so thoroughly in the production system that its origins were largely forgotten by the people who relied on it. The most striking thing about the Huck Rivet's impact is not that it worked. It is that, on the other side of the war, the same fundamental problem went unsolved. Germany in 1944 had a labor crisis that paralleled the American one, but was, in absolute terms, considerably worse. The German economy was running on forced labor. French and Polish workers, Soviet prisoners of war, concentration camp inmates contracted out to industrial firms because the German military had drafted essentially every able-bodied man capable of operating a rifle. The factories building Messerschmitt fighters, Junkers bombers, and the new Arado jets were staffed by workers who had not been trained for aircraft manufacturing, who often did not speak the language of the supervisors, and who in many cases had no incentive to produce quality work for an enemy state holding them captive. The result, by mid-1944, was a quality crisis that the German aviation industry could not control. In July 1944, Captain Dieter Lukasch, the Austrian-born Luftwaffe officer who took command of the world's first operational jet bomber unit equipped with the Arado AR-234, reported on the aircraft his squadron was receiving from the factory. Lukasch's words, repeated in post-war German aviation histories, are precise. Hardly any aircraft arrived without defects, and the defects covered all systems. He attributed the problem to hasty completion and shortage of skilled labor in the plants. He was not exaggerating. In June 1944, Messerschmitt's main development office at Oberammergau filed an internal complaint about production line Me-262 jet fighters. Workmanship on armament hatch covers, sheet steel cockpit components, engine cowlings, and surface finishes was poor. By February 1945, Messerschmitt's chief test pilot Fritz Wendel was filing reports of severe technical problems caused by quality control failures. The German aviation industry had reached the point of trying to teach its workers what good workmanship looked like by displaying captured wing sections of shot-down American aircraft inside German factories, using the enemy's manufacturing standards as an aspirational training aid. What the Germans were missing was not skill, it was not engineering capacity, it was not even in absolute terms raw materials, although those were certainly running short. What they were missing was the technical solution that allowed unskilled labor to produce structural-grade aircraft joints. They had not invented the equivalent of the Huck Rivet, they had not adopted it from elsewhere. The riveting in German aircraft factories in 1944 was being performed essentially the same way it had been performed in 1939, by buckers and hammerers, working in pairs, requiring access to both sides of every joint, demanding skill that the available workforce did not have. The German engineers were not stupid, they were among the best in the world, but they were committed to a manufacturing paradigm in which the fastener was a small detail to be solved by trained workers, rather than an industrial bottleneck whose technical specification could be redesigned to remove the need for skilled labor entirely. The Huck Rivet was an answer to a question the German aviation industry had not asked because it had not understood that the question was the right one. By the time the production crisis became operationally lethal, when jet bombers were being delivered with defects in every system, it was too late to redesign the fastener, retool the factories, and retrain the labor force. The war ended before the cycle could complete. The Huck Rivet did not win the war. It is too small a thing to be credited with that. But it is one of those small things whose absence would have changed the arithmetic of victory in ways that would have rippled outward. If Ford could not have built one bomber every 55 minutes, if Willow Run had been forced to operate at Consolidated's pre-war pace of one every several days, the 8th Air Force in Europe would have had fewer aircraft. The strategic bombing campaign against Germany, which depended on numerical superiority to absorb the brutal attrition of daylight raids over defended airspace, would have run more thinly. The Pacific bombing campaign, which depended on the long range of the B-24 to reach Japanese targets from Australian and Pacific bases, would have been smaller. The total weight of American air power dropped on Axis territory between 1943 and 1945 would have been measurably less. Whether this would have changed the eventual outcome of the war is impossible to say with certainty. The Allies had several strategic margins of safety, and the war would probably have been won on slightly different terms. but the speed at which it was won, and the number of American and British aircrewmen who survived because their bombing missions could be flown in larger formations with better mutual protection, those numbers would have been different. And small differences in those numbers translate on the scale of a 4-year industrial war into thousands of additional dead men. The Huck Manufacturing Company itself did not become famous. The American public then and now has not generally recognized Louis Huck's name. The riveting industry is not glamorous. The companies that build screws and bolts and rivets are the kind of industrial concerns that operate in the background of public consciousness, supplying the components that more visible companies use to build the products that get the headlines. Huck himself continued to innovate after the war. The U.S. Navy approached him with another problem, fasteners that loosened under sustained vibration in combat aircraft, and his response was the Huck lock bolt, a new fastener system that became standard on military aircraft and is still in use today. The company evolved, was acquired, became a division of larger industrial firms, and eventually became part of Howmet Aerospace, where Huck-branded fasteners are still manufactured for industries ranging from aerospace to railway to construction. What the story preserves, when you strip away the wartime drama and the Willow Run mythology, is something quieter and in its way more important. The idea that the bottleneck in any large industrial process is rarely the thing that the headlines focus on. It is rarely the engine or the airframe or the avionics or the strategic doctrine. It is, more often than not, some unglamorous small component made by some unglamorous small company whose redesign unlocks capacity that the rest of the system could not previously access. Louis Huck did not set out to win the war. He set out to solve a riveting bottleneck he had observed in a German factory in the early 1930s. The bottleneck happened, by historical coincidence, to be the same bottleneck that the entire American aviation industry would find itself standing in a decade later. He had the answer. They had the question. The match between the two, more than any single act of strategic brilliance, was what allowed Willow Run to become what Charles Lindbergh, visiting the plant as a consultant, called the Grand Canyon of a mechanized world. There is a metric used by industrial historians that measures the productivity of a manufacturing process by the unit of time required to produce one finished good. For the B-24 at Consolidated's San Diego plant in 1941, that figure was on the order of one airplane per several days. For the same airplane in Willow Run in April 1944, it was 63 minutes. At absolute peak, 55. That difference, the compression of production time from days to less than an hour, was not the result of a single breakthrough. It was the cumulative effect of dozens of decisions. The assembly line layout, the breakdown of the airplane into subassemblies, the standardization of parts, the steel dies that replaced soft metal dies, the moving conveyor system, the federal investment that built the largest factory under one roof in human history. Each of those decisions contributed. Each was necessary. But somewhere in the middle of that cumulative effect, smaller than any of them, there was a fastener the size of a fingernail that allowed an untrained 18-year-old woman to install a structural-grade joint in 1 second from one side of a wing panel with a tool that she could be taught to operate in a single afternoon. Without that fastener, the assembly line still works, but the riveting stations slow it down. Without that fastener, the women on the floor at Willow Run are limited in what they can do because the bottleneck pieces of the work require skilled buckers who do not exist. Without that fastener, the bomber and hour math does not close. The Germans, working on the same airplane problem in the same window of time with the same labor crisis, did not have the equivalent. Their factories produced jet bombers in 1944 that arrived at operational squadrons with defects in every system. Their manufacturing crisis was visible in the testimony of pilots, in internal Messerschmitt memos, in the desperate display of captured American wing sections inside German factories as training material. They were trying to teach their workers how to build airplanes the way the Americans built them, without understanding that the Americans were not building them with skill. The Americans were building them with a fastener that did not require skill. That is the asymmetric advantage that the historical record preserves about Huck's work.
It is not that the United States had better engineers, better workers, or a better strategic vision. It is that in one specific corner of the industrial ecosystem, an American small businessman had patented a solution in 1936 to a problem that nobody else fully understood would matter in 1943. When you look at the wars and technological transformations that have come since, the Cold War, the space race, the digital revolution, the supply chains of the 21st century, it's worth asking, quietly, where the equivalent invisible solutions are operating right now. Some unglamorous small component made by some unglamorous small company that nobody is paying attention to, that is quietly determining whether some future capability is possible or impossible. The Huck Rivet was that 80 years ago. There's almost certainly something playing the same role today. The question is whether anyone notices. Are there any Huck Rivets you've encountered in your own work? Small, unglamorous solutions that quietly unlocked something much larger? Tell us in the comments. And if you know a veteran or descendant who worked at Willow Run or any of the other arsenal of democracy factories, share their story. Those people built the airplanes the historians write books about, and their experience deserves to be remembered.